How many people here have ever held a gecko? Okay, 37. Okay, good. Let me ask you this. How many people, do you have any idea how many species of geckos there are? There are 800 species of geckos. Clearly the gecko doesn't have the same notoriety as lions and tigers and bears, but it definitely captures our imagination a little bit because it's the largest animal on the planet that can climb up a wall and across the ceiling. This beautiful lady smiling at you, her name is Big Mama. She resides in my colleague Duncan Urshick's laboratory. Duncan's a professor at UMass Amherst. Duncan has been studying geckos since he was in graduate school. To my knowledge, we're the only gecko adhesion team in the world that actually has a gecko biologist as part of the team. That's going to be a substantial part of my speech today. The objective for today's speech is to walk you through the process, the journey, the biomimicry journey that we're taking from an animal, so we're going to talk about the animal for a few minutes, to technology and on to products. Technological hiatus. So if you watch this creature climb a wall and you look at it and say just how effortlessly it climbs up a wall, I don't know if you've ever seen this. How many of you have ever watched this animal? And you think, if I could derive a technology from the abilities of this animal, what would be the attributes of such a technology? You'd want it to be what we've written. It should be able to climb on multiple surfaces, reusable, shear and normal loading, minimal energy loss. So these are the attributes that we are emulating with GECSkin. GECSkin is the name of our technology. The company is Felsuma, and we are commercializing and bringing through this biomimicry world this technology called GECSkin. Let me ask you this. Have you ever sat in a room with a gecko biologist and a polymer scientist? I hadn't either until I met these two gentlemen. And then it made me wonder how many times you and I pass in the hallway or have a cocktail party with somebody from a totally different discipline, a historian or a mathematician or an engineer or a political scientist or a philosopher, and we say, gee, I really don't have anything in common with that person. Think again, because you just might. Several years ago, Professor Crosby, was sitting in his laboratory with his students, and he wondered, Al's a political scientist, and he wondered, I wonder if anybody's ever measured gecko adhesion before. So he was looking through the literature, and sure enough, he found a paper by Professor Urshick, wherein Professor Urshick had actually quantified gecko adhesion. So Al said to his students, we got to find that guy. Where's that guy? It turned out, in the entire world, that guy was across campus from where Al Crosby was sitting. If you ever find yourself in a place where the entire world is turning left, and you say, I think we should go right, take a look at that, because there might be something there. And I say that because all the other researchers out there who are looking at gecko-like adhesion have decided that the key to a gecko's mobility are the hairs on the bottom of its foot, hairs called setae. Now, the hairs are important. We would say they're necessary, but they're not sufficient. What the hairs do is they create a bond. They definitely create a bond with the surface. They drape the surface and create a bond. But our solution goes further. Our solution is more mechanical, it's more systemic, anatomical. Let's say you're a person who weighs 67 kilograms, and you want to do a pull-up. Grab onto a bar, pull yourself up. You're pretty much producing a force of about 100 kilograms. A tokay gecko, this animal on the left of the screen, a tokay gecko on a pane of glass can produce force that's 40 times its weight. So to you doing a pull-up, that would be 2,700 kilograms. So a minute ago you were using a bar, try doing it on a pane of glass. There's a reason why the military and governments have been investing in this technology, millions and millions of dollars for years to try to figure out how do we mimic this capability. But how does a gecko do it? So I mentioned the hairs, fine, that's a good start, that creates the bond. The gecko also has, and you can see it a little bit on the picture on the right, it has a very stiff tendon. You and I have tendons that attach muscle to bone. the gecko has a tendon that extends all the way, integrates into its toes up to its skeletal structure. It's a very stiff material. So we have the bond combined with this anatomical structure of the tendon. The tendon is distributing the animal's weight across its feet. So we have a basic mathematical equation that we use that equates our technology with the gecko. We're measuring force capacity on the left side of the equation. Force capacity is the maximum load that any given material will hold in application. You'll notice van der Waals forces. Van der Waals forces say if two surfaces are very close together, they'll attract. In our equation, van der Waals forces are a constant. The variables are area and compliance, which I'll talk about in a minute. So we're manipulating area and compliance. Van der Waals forces is a constant. Once you've established the bond, it is what it is. Today we're measuring force balance. In the future, we'll bring time into it and we'll begin to measure energy balance. But just take a quick look at the equation, because the non-intuitive part of this equation, for anybody who's studied classic adhesives, is notice that compliance is in the denominator. So if compliance goes down, force capacity goes up. I'll say it differently. The stiffer the material, the stronger the device. And that's not intuitive to anybody who's studied classic pressure-sensitive adhesives, such as Scotch tape. So we needed to think about the idea of creating a stiff substance, a stiff material, one that would also drape. That's fabrics. Our devices are made out of fabrics and polymers. That's it. Those are the raw materials. Highly scalable, off the shelf. Fabrics and polymers. So fabric will drape a surface. That pretty picture is frosted glass. So fabrics can drape, but if you pull a fabric tight, then you have a stiff material. So imagine, back to my pull-up example, you're exhausted, but you want to do one more pull-up. And I said, well, you can have a glove or you can have a strap. What would you like to help you? And the answer is both. You're going to want a glove to maintain the bond, but you're going to want a strap to amplify the capabilities of your limbs. That's what we're doing with GECSkin. We're simplifying a complex problem, a very complex problem. We can understand that there are so many designs, and we are now beginning to understand the designs, and we can tune. I'll explain tune to you. We can tune our designs for endless applications that our customers are now bringing to us. What are their needs? What are their applications? So this tuning concept, this is fascinating. You got to make sure whatever you're working on continues to fascinate you. So we knew that this would happen. It had happened in the laboratory. But once we had shifted over to commercial materials, then watching this data unfold was a fascinating process for us. We are working on customer projects, and we're plotting, according to that mathematical equation, the attributes, the performance of these materials. What you see here is a plotting of polymers, just polymers, plotted, again, on the premise of the mathematical equation. And you can see that now the performance of different polymers starts to come out based on that equation of thinner and stiffer, higher peel. We can't quite predict yet how polymers will behave, but we're learning very, very quickly. One thing to note, if you see the full data set, all the silicones do not hang together, and all of the acrylics are not all together. They're spread out depending on each polymer's attributes. The word gecko, we use the word gecko. Before I mentioned to you, there are 800 species of geckos. So can we really just say the word gecko? Nature has already demonstrated a multitude of designs. These are gecko's feet. Nature's already demonstrated a multitude of designs that have evolved to meet environmental needs. We at Felsuma are just now realizing that we're in the process of developing what will become thousands of designs. Beginning portfolio today, but it's going very, very quickly based on what we're learning from customers. So we're learning to adapt to different surfaces, but also we have the beginning of a portfolio. This is Kevlar. This is, and not surprisingly, this device mimics the anatomy of a gecko. We have an anatomy, pad, skin, and this is the tendon. This is a piece of drywall, just simple drywall, but the idea being we can attach this, and if you pull down and shear, this will hold 2-3 kgs. It'll pop off at about 10 kilograms. But it's meant to and designed to hold about 2 or 3 kilograms just in sheer force like this. But the beauty is, of course, we can peel it off, put it on again, peel it off, and put it on again. Where it gets a little interesting is then, as I like to say, we go into 3 dimensions. So now, once again, pad, skin, and tendon, but now we have 2 pads, 1 tendon. One pad is facing this direction, and the other one is facing you. So I can apply one pad here, and then I can gladly sacrifice my phone with great surety. And in so doing, it's a simple demonstration, but the beauty of this is it's an independent device, and furthermore, keep in mind in terms of this word tuning, we can tune the different sides of the pads for different surfaces. One can be tuned for glass or wood. Obviously, we have some that'll work on multiple surfaces, but the idea of being able to tune for different surfaces, as well as then being able to have an independent device that's tuned for a specific application or applications, where we can connect things that can't be connected today. So this is my colleague Vincent, who still in his human form is acting like a gecko. When we had started to use commercial materials, and he's using a piece of carbon fiber. I've shown you Kevlar. Kevlar, the white piece was nylon. Vincent is using carbon fiber. He's in a chemistry laboratory. He's just attaching it to the hood in the chemistry laboratory. But as soon as we moved over to commercial materials, we wanted to see, could this still scale up the way this technology is intended to do now with new materials that we can take to manufacturing. So Vincent's a brave fellow, and he said, I'll do it, and off he went. And he's demonstrating the concept of being able to attach, peel, hold a weight, attach, and peel. So I'm the CEO of Felsuma, and one of the biggest points of nervousness for a CEO is when you look at a cool new technology and you think, oh man, what are the applications here? Well, that nervousness dissipates very quickly once you engage customers and customers explain, these are the applications, these are the needs, here's how we're going to bring this to market. That's how we're doing it. I've told you that Gecko skin is very much a systemic solution. We also asked ourselves, can this have a systemic, can the value chain, the supply chain, can the supply chain also be systemic sustainably? So the raw materials that we're using, polymers and fabrics, we have the ability to reduce, if not eliminate, hazardous substances. We're using mature existing manufacturing processes that are becoming ever cleaner. And certainly the concept of reuse of these is one of the biggest factors in eliminating waste. So look at all those current tools that you and I use. You and I have accepted some very, very bad habits. And for example, we're willing to put up with smashing our thumb with a hammer. We're willing to put up with tapes that are so sticky you can't use them and they leave a residue on the surface. Glues that are very messy. But the real question is, what's the real cost of a nail, a tape, some glue? The markets represented by these products are over 30 billion euros a year. But that's the beginning of the story. Then we have the disposal, because these are all one-time use items. So you have the disposal cost. But the real hidden cost is to repair the damage that they leave behind. Where are we going with all of this? So from adaptation to evolution, from force to energy, the difference is time, the gap is time. Today we're dealing with force, tomorrow we'll bring time into it, and we'll move to energy. So what will that allow us to do? That will allow us then to make materials that will sense their surface and adapt to them. We'll be able to make materials that are from bio back to bio. We'll be able to use computational physics that will learn from evolution. So today we're making designs with customers, but going forward, it's an endless set of design possibilities, material possibilities. So the goal of today's talk, as I told you, the objective was to walk you from an animal to a technology to products. We have a B2B business. We work with corporations on a one-by-one basis. We're very selective of the corporations we work with. We don't have a website launched. If you're interested, please feel free to contact me. We'll launch our first consumer product on the web within the next 1 year. Again, if you have an interest in that, please contact me. But big picture, the reason why we're here is that we have a unique opportunity. We, Felsuma, have an opportunity, along with our customers and our vendors, to think like Gecko, think in 3 dimensions, think about sustainability. And if we can do that, then we have an opportunity that will encompass what a Gecko will teach us about living sustainably on Earth. Thanks very much.